Hello, welcome to the lecture number 20 of the course Quantum Mechanics and Molecular Spectroscopy. We will go on with our lecture after a brief recap of the previous lecture. In the previous lecture we looked at two things, one is the rate of absorption and other is rate of emission. Based on this we got two equations, rho radiation nu is equal to A21 divided by P12 N1 by N2 B21 minus. Okay. And this under the circumstances A21 is written as A and P12 equals to B21 is equal to B. We write A by P N1 by N2 minus 1. Okay. Now, N1 by N2 is given by Boltzmann population, this is equal to e to the power of h nu by kT. This is same as e to the power of delta E by kT. Okay. So, this turns out to be A divided by P into e to the power of h nu by kT minus 1. Now, rho radiation nu, if I look at in terms of Planck's black body radiation, that will give me 8 pi h nu cube by c cube into 1 over e to the power of h nu by kT minus 1. Okay. Now, if I rho radiation nu and now if I equate these two equations, then I can get A by B equals to 8 pi h nu cube by c cube, and we also discussed that A by B is proportional to nu cube. Okay. And another thing that we looked at, if you starting from the Fermi's golden rule, okay, and using dipole moment along z axis and also using isotropic light, we said that W12 is equal to pi by 6 h bar integral 2 mu z dot E 1 modulus square rho 2, okay, and this is nothing but here dipole moment and this is density of states. Okay. Now, I want to use this equation and get along. Okay. Now, there is something that is there is that if I have this also can be written as, okay, W12 can also be written as pi by 6 h bar 2 mu z to epsilon, okay, 1 modulus square, and then I will get the electric field out square of it rho to E. So, this is okay, this is probably not the right way to write. So, this one can write as pi by 6 h bar 2 mu z. So, only the component of mu z that is aligned with respect to the electric field I 1 square square rho 2. The reason why I want to bring the electric field out, because the energy of electromagnetic field E, okay, is equal to epsilon naught E square. Okay. So, this is energy and this is nothing but electric field, and epsilon naught is permittivity of free space. So, I can rewrite this equation W12 equals to, okay, pi by 6 epsilon naught h bar modulus of 2 integral to mu z epsilon 1 square E rho 2. Of electromagnetic radiation. Okay. Now, so this is what we have. Now, what I want to do is I want to slightly, now this is based on Fermi's golden rule. And you know, Fermi's golden rule happens because there is a density of states. It is going from a discrete initial state to state that is embedded, okay, in some density. Okay. But now let us consider, for example, you have initial state 1 and you have final state 2, okay, which is embedded between in some density, but I want to look at only this transition. Okay. So, I am looking for 1 to 2 discrete transition. Okay. No density, it is just the discrete transition. Okay. Now, apart from that, when you are looking at this discrete transition, okay, now all I want to do is I do not want to use, so this will happen, let us say it happens at delta E 1 2 or 2 1, this is equal to E H nu 1 2. Okay. It will happen at a very specific wavelength or a very specific frequency nu 1 2. Okay. So, if I want to make a discrete transition, if I want to go from state 1 to state 2, I have to give the right frequency nu 1 2 or the electromagnetic radiation with the right frequency nu 1 2. But now if you look at, we were talking about the candle or some kind of lamp. So, of course, that is not going to give you a monochromatic energy or electromagnetic radiation. So, nu 1 2 will not be very selective. Okay. You will get all sorts of nu, and out of which only nu 1 2 will cause the transition. Now, if you use non-monochromatic light, okay. So, what I am trying to do is that I am going from state 1 to state 2, which has a energy difference of delta E and frequency of nu 1 2, okay, but using non-monochromatic radiation. And when you have non-monochromatic radiation, you have, let us say, P radiation nu such that you have nu plus T nu in the frequency nu plus T nu. Okay. Now this is the radiation density. Okay. So, if I want to get the energy, okay, rho radiation nu, I should get P radiation nu d nu. Okay. If it is a small integral, but if you have a large integral, then this should be integrated over nu. Okay. Now, in such scenario, okay, your W12 will be equal to pi by 6 epsilon naught h bar 2 mu z e 1 whole square, okay, energy E with radiation density P radiation P radiation at mu. Okay. But we are looking at spreading the radiation, so this must be integrated over d nu. Okay. So, when I integrate over radiation mu nu, so what I will get is pi 6 epsilon naught h bar 2 mu z epsilon 1 whole square integral, okay, by the E P radiation nu d nu, of course I am writing the same equation. So, when I integrate, what I will get is this integral is given by 1 over h bar rho radiation. Okay. Therefore, your W12 is given by pi by 6 epsilon naught h bar square integral to mu z along some epsilon 1 modular square into rho radiation. So, let me reiterate. Now, according to Einstein's coefficients, what was rho W12 rate for absorption? It was nothing but B12, okay, N1 rho radiation. Okay. Now, I can equate these two equations. Now, so what you will get? Then B12 N1 equals to pi by 6 epsilon naught h bar square 2 mu z 1 whole square. Now, but there is a problem in this equation. I do not know what this N1 is. N1 we said is the population of the state, but when you derive quantum mechanics rules, okay, we derive for one single molecule or one single quantum object. So, your N1 must be actually 1, because all this derivation of this, the initial state to final state, is based on one quantum object. So, therefore, N1 v must be replaced by 1. So, your B12 is nothing but your B is equal to pi by 6 epsilon naught h bar square plus 2 mu z epsilon 1 whole square. Okay. So, let me look at, so your B, that is your Einstein's coefficient for spontaneous absorption and stimulated emission, is given by pi by 6 epsilon naught h bar square and the integral 2 mu z modulus square. But we also know A by B is equal to 8 pi h mu cube by c cube. Okay. Now, we know that h bar is equal to h by 2 pi or h is equal to 2 pi h bar. So, if I write in terms of h bar, then I will get 2 pi is, so you will get 16 pi square h bar nu cube by c cube, that is A by B. But now we already know B, so A is equal to 16 pi square h bar nu cube by c cube into B, which is nothing but pi by 6 epsilon naught h bar square 2 mu z 1 square. Now I can do some arrangement. So, this h square and this h bar will go away, this pi becomes pi cube, 6 2 times, so 3 8. Okay. So, this will become 8 pi cube by 3 h bar c cube nu cube 2 mu z square. So, your A is given by this and B is given by. So, what you have is A is some constant 2 mu z epsilon 1 whole square and B is some other set of constants 2 mu z epsilon 1 whole square, and these constants here will be 8 pi cube nu cube divided by 3 h bar c cube, and this constant is pi by 6 epsilon naught h bar square. Now you can really see that the Einstein's coefficients A and B are proportional to the square of the transition dipole. So, both A comma B are proportional to 2 mu z 1 square of this. So, this is nothing but transition dipole. Okay, the proportionality constants are different, but essentially they are proportional to transition dipole. So, if you know the transition dipole, then you can get the Einstein's coefficients A and B, and if you know the Einstein's coefficients A and B, then you know the rate of absorption and rate of emission. Okay. So, essentially the rate of absorption / emission is related to the transition dipole. Let us suppose you have an excited state, ground state 1 and excited state 2, and you have N1 and N2. Okay. Now, if you excite, okay, from ground state to excited state for a very large delta E, and we know as the large delta E increases, nu also increases, or very large nu, which means your A by B is proportional to 1 or proportional to nu cube. That means if you have very large nu, okay, the nu cube will be much more than the B. So, for example, let us say nu is 100. Okay. So, let us say nu is equal to 100. Okay. So, nu cube will be 100 cube. So, that will be 6 zeros. So, you have nu of 100, okay, the nu cube will be a million. Okay. So, generally nu cube is going to dominate over nu. That means A will dominate over B. That means spontaneous emission will dominate over stimulated emission. So, which means for a very large delta U, okay, spontaneous emission will dominate over stimulated emission. Okay. Now, you can think of a scenario in which you are going from a state 1 to state 2. Okay. Your initial population is 1 and this is N2 at some point of time, okay, after you excite, and then you switch off the light. Then what will happen? Everything will emit spontaneously. So, minus d. So, decay of population from the excited state dN2 by dt should be proportional to the N2 times A, that the rate constant and the population. Okay. Now, if I integrate this, minus d N2 over 1 over N2 is equal to A dt. Okay. So, you can take the other side, dN2 by N2 is equal to minus A dt. So, this will be nothing but ln N2 will be equal to minus AT. So, if you take plus some constant of integration, and when you rearrange, what you will get is N2 of t will be equal to N2 of 0, that is initial, okay, exponential minus AT. Okay. So, this is, so the decay will be given by A, decay constant will be given by A. Okay. So, what means the decay constant, when you excite the molecules to this higher level, the spontaneous emission will decay by rate constant of A. Okay. Now, this decay constant A is equal to some constants 2 mu z epsilon 1 square. This is nothing but your decay constant. Okay. So, by measuring the decay constant, and this can be experimentally measured, I will come to this in the next lecture. Okay. Okay. Decay constant in the excited of the excited state can be measured. So, it is like a rate of reaction, okay. Then you can measure the rate constants, that is a decay constant, and that decay constant is proportional to the transition dipole. So, if you can somehow measure the decay constant experimentally, then you can evaluate the transition dipole. Okay. We will stop here and continue in the next lecture.